Welcome to the deep dive. Ready to explore something shocking?
You bet.
Today, we're diving into the world of electrostatics.
The science behind stationary electric charges.
Exactly. So, those times you get a little zap, touching a doorknob, or see lightning flashing across the sky.
That's electrostatics in action.
Okay, let's start simple. Positive and negative charges, they're like tiny magnets, right?
Attracting and repelling.
But how do they exert force when they're not actually touching?
It's all about Coulomb's law.
Coulomb's law.
Think of it like this. Every charge has an invisible force field around it.
Okay, I'm picturing it.
Any other charge in that field feels a push or a pull. Coulomb's law says the force is proportional to the product of the charges.
So bigger charges, bigger force.
Exactly, and it's inversely proportional to the square of the distance between them.
Like gravity, the further apart, the weaker the force.
You got it. Now imagine you put something between those charges.
Like a sheet of glass.
Yeah, or plastic. These are called dielectrics. They can actually weaken the force.
So if I put something between two charges,
The force changes.
even though they're not touching,
Right.
how does that even work?
Dielectrics store electrical energy internally.
So it's not just about the charges themselves.
It's about the space between them, too.
That leads us to the electric field, right?
You got it. It's like a map of the electrical influence around a charge.
Showing how it would affect another charge nearby.
Exactly.
So if we put a positive test charge near a big positive charge,
It would experience a repulsive force.
trying to push them apart.
Right. We measure that push or pull with electric field intensity, or E.
The force per unit charge.
Yes. Now, things get trickier with multiple charges or even a continuous distribution.
How do we calculate the electric field then?
It's like a group of friends pulling on a rope.
Okay, I'm listening.
To get the net force, you need to consider each individual pull and then combine them.
So we break it down.
Exactly. With multiple charges, we calculate the field for each one and add them up.
Taking into account the direction.
Right. It's called the principle of superposition.
What about when charges are spread out continuously?
Like on a charged rod,
Yeah.
we treat a tiny piece as a point charge and then integrate over the whole thing.
Okay, so bring it down and add up the contribution.
You got it. Whether it's individual charges or continuous spread, the takeaway is...
A charged particle always feels a force in an electric field.
Exactly. But can we actually see these fields?
That's what I was thinking.
We can't see them literally, but we can visualize them
How?
using electric lines of force,
Were those?
imaginary lines representing the direction and strength of the field.
Okay, so it's like a map.
Exactly.
Yeah.
And they have some interesting properties.
Like what?
They always start at positive charges and end at negative ones.
Like positive charges are emitting these lines.
And negative charges are absorbing them.
Cool.
And crucially, these lines never cross.
Why not?
The field can only point one way at any given point.
So no tangled lines.
Exactly. Now, the density of the lines, that tells you the field strength.
More crowded the lines, the stronger the field.
You got it.
This is a really helpful way to picture it. But how do we measure the amount of electric field going through a surface?
That's where we talk about electric flux.
Okay, tell me more.
Denoted by phi, it's like how much water flows through a net in a river.
Okay, I see.
The flow strength, like field intensity, and the area of the net, the surface, determine how much gets through.
So a larger surface area or a stronger field means greater flux.
Precisely.
Hmm.
And this leads us to Gauss's law.
Gauss's law.
It connects the flux through a closed surface to the total charge inside.
So we can relate the field passing through to the charge strapped inside.
You got it. And Gauss's law is incredibly powerful.
How so?
It simplifies calculations, especially for symmetrical charge distribution.
Sounds like a handy shortcut.
Absolutely. Now let's shift gears a bit and talk about energy.
Okay, I'm ready.
Charges exert forces, and forces can do work. So where does energy come in?
Yeah, I'm curious about that too.
That's where we introduce electric potential and potential energy.
Electric potential.
It's a measure of potential energy per unit charge at a point.
So how much energy a charge would have there?
Exactly. Like being at the top of a hill. Higher up, more potential energy.
So if we know the potential at different points, we can figure out the work to move a charge between them.
Yes. We can calculate potential for various charge distributions.
Just like with electric fields.
Right. We're building quite the toolkit for electrostatics now.
It's all coming together. Now, what about those electric dipoles we talked about earlier?
Those equal and opposite charges close together.
Yes, those What makes them so special?
Their electric field and potential behave in unique ways.
So their influence changes depending on where you are.
Exactly. They also experience force and torque in an external field.
Like trying to find a balance.
Precisely. Now, we need to talk about conductors.
Conductors.
Materials where charges can move freely.
Like metal.
Right. And this freedom of movement leads to some unique properties.
Like what?
Any excess charge on a conductor goes straight to the surface.
Wait, why the surface?
They repel each other until they can't go any further.
Like penguins huddled against the wall.
Exactly. This also means the electric field inside a conductor is zero.
Zero. Why?
The charges would redistribute to cancel out any internal field.
It's self-regulating.
Exactly. And the potential inside is constant, equal to the surface potential.
Amazing.
It is. Now, let's take a break and recharge. We'll be back with more electrostatics soon.
Sounds good. I'm ready to dive deeper. Back for more electrifying insights. That first part, wow.
It's just the beginning. Ready to talk energy.
Absolutely.
Yeah.
I want to know how we can actually harness the power of electric fields.
Well, you have to realize electric fields store energy.
Really?
Think of stretching a rubber band.
Storing potential energy.
And when you let go, that energy converts into kinetic energy. Same idea with electric fields.
So separating charges stores energy in the field itself.
Exactly. And we can actually quantify that energy.
How?
For a simple parallel plate capacitor, it's proportional to the square of the voltage and the capacitance.
Hold on. Capacitance. What's that?
Think of it as a system's ability to store charge. Like how much charge a capacitor can hold at a given voltage.
So it's a measure of capacity.
Exactly. And it's related to the physical characteristics of the capacitor.
Okay, so the size and spacing of the plates.
Exactly. Larger area means more charge. Closer plates mean stronger field, higher capacitance.
So we can tailor the capacitance by changing the design.
Right. Now, how do we charge a capacitor?
Good question.
We connect it to a voltage source, like a battery.
Okay.
The battery moves charges from one plate to the other, creating that electric field.
So the batteries are like a pump, storing energy in the capacitor.
You got it. And when we discharge the capacitor, those charges flow back, releasing the energy.
Wow. So capacitors are key for storing and releasing electrical energy.
Precisely. Now remember dielectrics. They reduce the force between charges. But when placed between capacitor plates, they actually increase capacitance.
Really? How does that work?
It's counterintuitive, I know. But think of it like replacing air with a denser material.
So we can pack more charge in.
Exactly. We measure this effect with the dielectric constant, kappa.
So higher dielectric constant, bigger capacitance boost.
You got it. The choice of dielectric is really important.
Fascinating how these microscopic properties affect the big picture.
Absolutely. Now let's get back to conductors. We know excess charge goes to the surface.
Right, the penguin analogy.
But that distribution isn't always uniform.
Oh, I thought it would spread out evenly.
True for perfect spheres, but real conductors have irregular shapes. Charge concentrates at sharp points.
Why is that?
It's about the field lines. They're more concentrated at points, meaning stronger field. And stronger field means higher charge density.
So the field is squeezing more charge onto those points
That's a good way to think about it. This explains why lightning rods are pointed.
to attract the lightning.
The concentrated charge creates a strong field that ionizes the air, creating a path of least resistance for the lightning.
So we can direct lightning strikes using this principle.
Exactly. Now, inside a conductor, the electric field is zero. But what about potential?
Fill me in.
It's constant everywhere, equal to the surface potential.
So no matter where you are inside, same potential energy per charge.
Precisely, like being inside a Faraday cage.
Shielded from the outside electric field.
Exactly. Okay, let's take another break. Still lots more to uncover.
I'm hooked. Ready for the final charge. Let's wrap up our electrifying deep dive into electrostatics.
I've saved the best for last. Remember electrostatic shielding? We just touched on it.
Creating a safe zone from electric fields. Yeah, that was pretty cool.
It's a key concept built on everything we've discussed. Basically, conductors block or redirect fields.
Like a force field.
Well, sort of. Think about it. The electric field inside a conductor is always zero.
Right, it's completely shielded.
Exactly. Anything inside a hollow conductor, a Faraday cage, is totally protected.
Like those anti-static bags for electronics.
That's one example. And remember those high-voltage transmission lines?
Yeah, they have a shield too, right?
A grounded metal shield. It prevents the strong fields from interfering with anything nearby.
And it stops the lines from losing energy. Double protection.
Exactly. Understanding charges and fields at work. Now, let's talk about something that happens when the field near a conductor gets super strong,
Super strong, huh?
especially at sharp points. It's called corona discharge.
Corona discharge.
Basically, the field gets so strong it ionizes the air.
Ionizes, like stripping electrons from the air molecules.
Right, creating a plasma of charged particles. This ionized air can then conduct electricity.
So the charge leaks away from the conductor.
Exactly.
It's like the field rips the air apart to let the charge escape.
That's a great analogy.
Yeah.
Now, corona discharge can cause problems in high voltage systems.
Power loss.
Yeah, but it's also used in things like air purifiers and photocopiers.
So it can be good or bad depending on how we use it.
Exactly. Control is key. This deep dive has taken us from basic forces to complex applications. It's all connected.
I know, right? We've covered so much ground. And to think this is just the beginning of electromagnetism.
Electrostatics is the foundation for so many other areas of physics and engineering.
It's incredible how charges and fields affect everything from circuits to light.
And that's what makes science so amazing. It's all about connecting the dots, understanding the basic principles.
And seeing how they play out in the real world.
Precisely. Keep exploring, keep questioning, keep that curiosity alive.
Great advice. Thanks for being such an awesome guide through the world of electrostatics.
My pleasure. Until next time, keep those minds charged up.
We'll be back with more deep dives into the mysteries of science. Stay curious.